Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is the fourth and final part of the series on RMS. In this video, we are going to look at the different versions of the previous videos, and we will discuss which one to use in which occasion. And then we'll talk about multi-channel. We will add support for multiple channels. Currently, our RMS meters are only measuring the levels on the first channel, that is usually the left channel on a stereo pair, but we are going to add support for multi-channel so that you can even have tracks with 16 channels if you wanted, or 64, up to 64 channels really. And then finally, we will be able to say goodbye to this series because we'll have covered everything, at least that I know about RMS and how to compute and how to use it. So let's jump right in. I have here in Reaper the effects that we have implemented so far open in front of me. And there are three different versions, one from each video. And what I want to discuss is when to use each version. So the one that I prefer is the optimized version. And it is as precise as the definitional one. And it is fast. It's not super hard to implement. And it gives you best results. It is the one that most people use. That's the one you want to start with. And usually it is not too intensive to store that window, so you can just store the window and it will be fine. And at the same time, it's not, I think, too many lines of code. I think it's almost the same amount of lines of code as the other versions. I mean, it's 5 lines of code. It's not that hard. Then, if for some reason that isn't what you don't want to keep a window of samples or squares of samples, for instance, then you can try the approximated version. Maybe you don't even care about the precision all that much, or you don't care about doing some shenanigans to find the right window size or the right coefficient that is going to give you the window behavior that you want. So maybe RMS approximated will be good enough for you. And it has the advantage of not needing a window. You don't need to keep a window of samples explicitly. And then there is the definitional one. When would you want to use it? I would say never, except maybe for this example, maybe because I wanted to show you the definition. Except for that, for real use, I don't think you ever want to use the definitional one. It is very slow to compute. It doesn't have any precision beyond what the optimized version would give you. So it is more like a way to understand RMS than really something that you could use. And again, why would you want to use RMS? We covered this in a previous video, sort of, but you would want to use RMS for meters if you are showing something. For instance, I have an auto-mixer plugin that shows you the levels of the channels, and this is being computed with RMS. So that's one reason why you would want to compute RMS, so you can actually show meters on the screen. That's one reason. Another reason is if you want to compute something that has to do with the levels of the channels, and that's the case in this plugin. I want to mix multiple microphones according to their relative volumes so that microphones that are contributing more to the signal have more gain allocated to them. So I want to know how much each microphone is contributing, and that means how much the level of each microphone is contributing to the overall level. So I compute RMS. And in this example here, in this plugin, I'm computing using the optimized version. And the original auto mixer, this is a modification on an existing plugin. The original one gives you 2 choices, the optimized and the approximated. They call it the efficient window. So here is the original auto mixer, and you can grab all of those in repack. So you have here the 2 window types, the rectangular and the efficient. The rectangular is what we are calling the optimized, and what they call the efficient is what we are calling the approximated. So there you have it. Those are the uses for RMS. Visualization and something that has to do with gain or levels. Now, let's move on to the problem of multi-channel. And let's start with the things you should not do, but they are the things that come to you first, so it's a good idea to talk about them. The first thing you should not do is add up all the channels without first squaring them. So if we look, for instance, let's say we are looking at the definitional one to begin with. Why not? So we could, instead of looking at the sample 0, we could loop over every channel and add up the samples. I am going to briefly sketch this code so you have an idea of what I'm talking about. So I'm going to start with channel -1, and I'll loop over the number of channels. And the first thing I want to do in the loop is add 1 to that variable. So this is a loop setup we have done many times before in all our plugins that are multi-channel. And I could have a variable here that is like samples, or really mix. I'm going to call it the mix of all the channels. And I can say that the mix is the sample at that channel. And then I divide by the number of channels. So I'm taking the mean of all the channels, and I could use that to calculate RMS. And that is actually a common idea. The original implementation of the automixer actually implemented RMS this way. And it kind of works most of the time. So it took a long while for people to realize that it was wrong. And eventually I figured that the implementation was wrong, and I contributed back a fix for this problem. So it is fixed in the current version of the original automixer. And of course, it is also solved in the automixer version that I developed. But the problem with this is similar to the problem we had in our first attempt to implement RMS back in the first video, when we just added a window of samples together without doing any pre-processing. We just added up the samples, and the problem was destructive interference. We had some parts of the wave above 0, some parts of the wave below 0, and those would cancel out. And that's something that may happen here if you have multiple channels. And now for something like an automixer that is dealing with microphones, usually people have mono signals and you would not notice this difference. But if you have multiple channels in which the signals are exactly the same but out of phase, and we talked about this in previous videos in this series as well, about the idea of how to invert a signal. And if you have a signal that is exactly the opposite of the other, then they are going to cancel out. But that's not how we perceive sound. If you think about it in the real world, if there are speakers that are sending signals that are out of phase, you still hear something because the air is still moving, and they may be canceling out, and there may be some weird interference, and if you move your head, you may hear some weird shifting of frequencies, but still you hear some sounds. So you can never say that the RMS of this signal is 0. So you don't want to do this thing we did right here. You definitely never want to just add up all the channels this way, and because of the problem of destructive interference. So let's not do this. And instead, what we're going to do is combine the channels after they have been squared. And this gets rid of the destructive interference problem like we did in the first video, because we are squaring, so we are getting rid of negatives. And when we get rid of negatives, we can actually combine the channels. So we want to do this after squaring, but before taking the square root. And this way, we are guaranteed to be combining the channels in the proper way. Here is another idea that is bad, okay? So this is another thing that I saw somewhere in some other plugin. I don't think it's a good idea. And that is to just take the maximum of all the channels. And that kind of sort of works. But the truth is that if you have multiple channels and one of them is just completely silent, that is not as loud as if you had two channels that were sending the same amount of air, the same amount of sound. So you would perceive them differently. So taking the maximum is a quick, crude fix. And if you have something like a compressor, you may not care about this. But it is incorrect to just take the maximum. What you want to do is actually combine the signals after squaring them. And then finally, another bad idea is to compute RMS for the channels independently. I mean, sometimes that may be a good idea depending on your use. If you are doing meters like these meters, then you may want to compute RMS differently for every channel. But for things like compressors or anything that has to do with dynamics, like the auto mixer I just showed, you don't want to you don't want to compress or to change the gain or to auto mix each channel individually. You don't want, after you compress the signal, for your left ear to be more compressed than the right or vice versa. You want the compression to be the same on both sides, even if the signal on one of the sides is slightly louder than the other one. So you want to combine using the technique I showed you, the technique of squaring all the samples first. So you combine all the samples and then you compute the RMS of all the channels combined. And that is guaranteed to give you good results with compressors and effects that have to do with dynamics. Okay, we covered the idea. Now let's implement this. And we have to implement it 3 times. On the approximated version, the optimized version, and the definitional one. And I'm going to go in this order. Approximated first, because it is simpler to implement in this version. So in the approximated version, what we are doing here is just feeding this RMS amplitude approximated. We have this moving average approximated. Yeah, that's where I want to start. So here we have the moving average approximated of the sample 0, and we are taking the square of that. But let's take our sketch here, and I'm removing this fix me because now we are going to implement this for all channels. So here we have the approximated, and I don't like the idea of having the word mix here, so I'll call this the sum of squares of channels. No, I don't like this. I think I'll have a mix. Mix approximated. And I'm going to rename this variable everywhere. But of course, as I said, we are not taking just the sample, we are taking the square of the sample. And now we have the mix approximated with, we are adding up the squares, and then we are dividing by the number of channels. So now instead of feeding the moving average approximated with the square of sample 0, what we're going to do is feed this with the mix approximated. And let me make sure that I change this back to sample 0 like it was before. So now I'm going to save this, and I want to look at the plugin working first, and then we'll do the setup for showing the problem with destructive interference, because I want to show that that problem occurs. It's not just a theoretical problem. So I'm going to do a setup with the tracks here to show that problem occurring, and then we'll move on and implement this multi-channel thing that we have. Okay, so I did a setup here, and I want to show you what I did. That is for demonstrating the problem of destructive interference if you do it the wrong way and just add the channels without first squaring them. So what I have here is the effect we created in a previous episode. It is the one that inverts the signal. And what I did here is I set this up so that the inputs for well, first of all, I changed the number of tracks on this channel. So now it has 4 tracks. It's the other way around. I changed the number of channels on this track. So it now has 4 channels. The track has 4 channels. And the signal is coming from a microphone, and it's going through this effect first, but I changed the pins so that it is taking the signal from my microphone and inverting it, but the output comes out of channels 3 and 4, as you can see here, coming out of 3 and 4. And now what comes into RMS is 4 tracks, 4 channels. This track has 4 channels, and the channels on the channels 1 and 2 are the signal coming in without inversion, and then channels 3 and 4 are the inverse of the signal. Okay, with that, I can come here to our plugin, and I re-implemented, I copy and pasted again the idea we had before of a mix of all the channels without squaring them. So I'm not going to square them. And now, without squaring them, here is the definitional slider. It's taking into account sample 0. If I paste in the mix, then you can see that it bottoms to 0, though there is definitely some signal coming through. Even if you invert some of the signal, there is still some signal coming through, so the RMS should not be 0, or the RMS should not be very low, minus 313 dB. It shouldn't be that. So that is the problem with doing this without first squaring the samples. So now that I showed you that it is a problem, I'm going to restore this. So now it's looking at sample 0 again, and we can come back down here to the approximated version. We have a mix approximated with the squares of all the channels, and now I'm going to change this so that instead of considering sample 0 or the square of sample 0, it's going to consider the mix approximated. And when I save this, now we can see that it is still moving almost the same way. It's not having the problem of destructive interference, though it's now looking at all the channels. So this is a proper multi-channel approximated version of RMS. Great. Now we have to implement the same idea for the optimized one and for the definitional one. The optimized one is not as simple as the approximated one because we have that square, that window that we have to keep around. And now the window should not be the square of sample 0, but the window should contain the squares. Effectively this, right? Effectively, that's what it should contain. It should contain the mix down of all the channels that have been already squared. But I definitely want to take the average, the mean, so I want to divide by the number of channels. So what if I just take this part of the code, move it up, because it will be useful in two different parts, and I'll say that this is mix multiple channels. Yeah, and I should say that this is a mix of the multiple channels squared. Mix squares, or actually the mean. So if RMS is root mean squared, then this is already the mean and the squares, the mean of the squares of the multiple channels. I'm going to rename all these variables so that they are not related to the approximated version, and we will reuse that on the optimized version as well. Okay, so I did that change. That was easy enough. Just renaming some variables, and then we have the mean squares of the channels, and that's what we are using here on the approximated version. And then we can just change this to use that as well. It has already been squared, so we don't need to re-square it. And it is already a mean of all the channels, so if we just drop this in here and save, then now we are considering multiple channels on the optimized version as well. For the definitional one, it's not that simple, because the definitional one is not storing the squares of the samples, and it's not computing a moving average of the squares of the samples. It's actually storing the samples, and then it's doing the squaring when it is doing the computation of RMS proper. So there is no good way for us to combine the channels before putting them in the window like we did with the optimized version, because it was already considering the squares, so we just put the mean squares of the channels here. That will not fly with the definitional one. So what we have to do for the definitional one is to store multiple windows, one per channel, and then we will compute here the definitional RMS, looping over the whole span of all the windows. And there is no better way to do this than to actually have multiple windows. So we will have to come back here to the definitional one when we are doing the setup of the window. And we're going to have to change this so it is using multiple windows. And the way I think about doing this is, what if we loop over the number of channels? So I guess I will have a loop that looks like this. So it's interesting, right? The definitional one is probably the easiest to understand because there is no shenanigans going on in the setup of the variables. Like, there is no weird formula like this one. Definitely no weird formula like this one. But for this particular problem of having support for multiple channels, the definitional version is probably the most annoying. Anyway, So I'll have the windows. It will be now the windows, because there will be multiple windows, one per channel. And it will start with 0. And then I need to store a bunch of windows. I need to store the window for one window per channel for the definitional version. And then I also need another window for the optimized. So I think it's now time to introduce more proper memory management, a better way to slice the big array that we have available to us. So here's how this is going to work. I'm going to say that there is the next free, or actually I'll just call it free address. And it starts with 0. And then we are going to be incrementing this when we get when we allocate more memory. So to begin with, the Windows definitional it will start with the free address, which is 0. And then it will add to the free address, which is to say I'm claiming this much of memory. So it's similar to memory allocation in the C programming language, if you're familiar with that. And how many slots do I want? Well, I want to have as many slots as I have channels. So I'll have, like, for this track, I'll have 4 slots on the Windows definitional. And then I'm going to loop over every channel. And then I will say that the Windows definition for a particular channel is equal to free address. And then I will increment the free address not with the number of channels, but with the window size in samples, because that's how many samples we want to store. So now we will be able to use Windows definitional at, for instance, channel 1, which is the second channel, the right ear. And if we want to look at the sample 100 that is stored in there, then that's how we can do it. So it is like a matrix or a multi-dimensional array that we're building here. But we are doing that with the bare bones assets that are given to us in JS Effects. So Windows definitional is now a matrix, and we still are incrementing this free address so that we can use it here later. In the Windows optimized, we were looking at the window size samples here as the address because we only had one window before, so the window optimized would be just this second window. But now we have to look at the free address, and also we want to do exactly this. We want to increment the free address with the window size in samples. And I'm doing this in one line. I'm also doing this in one line, and I'm doing this in one line because I think of these two operations as one, really. What I'm doing is I'm taking the free address and assigning it to the variable, but also I want the variable name and the size of that array to be on the same line. So that's why I'm writing this in this style. It's a style I developed. I think it makes sense. I'm also using a similar style when I'm doing loops. The whole setup of the loop is in one line because I think it makes sense together. Anyway, now we have this free address that is the next space where we are going to have something. So when we are doing the free mbuff, we look at the free address +1, which is the next index that is not being used. And then the Windows sum optimize is just a running sum. This is just a running sum. And this, or really a running moving average. And this is just a coefficient, so I don't have to do any memory management there. So now we have a definition of windows. We have multiple windows. When we are looking at the collection of samples, we don't want to just collect the first one. We want to collect all of them. So we are going to do a loop that is similar to this. Over here. And now we are looping over every channel. And for every channel on that particular window pointer, we are going to collect the sample that corresponds to it. So let's get rid of this. We're going to look at the sample for that channel. And of course, I want to get rid of this. So now we have the Windows definitional collecting for every channel on the particular window pointer that has been incremented here. Whew, that is a lot. Okay, now when computing the definitional version, we are looking at the squares of the samples, and I can just loop over the entire thing. So I can, instead of looping over just the first channel, I'm going to loop over all of them. So I'll call this the Windows sum definitional, and this will be the Windows index definitional, but I'll also have to loop over every channel. So I'll do a similar setup to the one from here, but I have to pay attention here because I was using this same variable channel here on the slider block, and that block of code only runs once when you change the slider or when you hit play or something like that. And then sample is running on every sample. But then the GFX block runs simultaneously in parallel, concurrently with the sample block. So these two blocks are running simultaneously. So I don't want to use the same variable I can use the same variable on the slider block and on the sample block because they don't run at the same time. This one runs first and only once. But the sample is running and the JFX is also running, and they may be running at the same time. So I want to have this as a GFX channel, maybe. How about that? GFX channel. And then so now I'm looking over the GFX channel, which is a different variable, so I don't run the risk of clashing because of the same variable name. And then for every channel, what do I want to do? Well, I want to do sort of this, right? I want to go over that window. So the Windows index definitional, actually, this is now only one window because we're looking at a window in a particular channel. So I'll call this the window index definitional. We will loop over the window size, and this is still the same as that, so that's good. And then the Windows sum definitional is I'm going to add the square of not only the window definitional, but the Windows definitional at that channel on that particular pointer. So let's change this. And I'm not using the window pointer, but the window pointer, the window index definitional. And now the rest is still the same. After I have computed the squares of everything, I need to not only divide by the number of samples, but I also need to divide by the number of channels because I'm adding things here from multiple channels. So I'll divide this by the number of channels as well. And I think that does it. Let's try this out and see. Okay, so we implemented the definitional one and it is working. You can see that it's going up and down with my voice, and it's similar to the approximated, though the approximated is going more slowly. But look at the optimized one. It is all over the place. We changed the definitional one and we broke the optimized one. The thing that is happening here is so subtle, it took me a long time to figure out. The problem is the following. We are doing the new memory management here with the free address variable. And you can see that this window optimized was supposed to be a high number. It was supposed exactly to be the number of channels times the window size in samples. That was what it was supposed to be. It was supposed to be a large number. But if I peek, you see that it's 0. And looking here in the debugger, the window optimized is 0. So the allocation is not really working. What's going on here? The thing is that this slider block is not running as often as we would like it to run. Here, I will create a debug variable that, as every other variable in JS effect, starts with 0. But I'm going to add 1 every time we run the slider block. That's a way for us to figure out how many times we are running this block. Now let's save this. And as you can see, we ran once, but we are not running every time we should. And when we ran this, after I saved this, and because I changed the block, the window optimized has been allocated. And when it does, you can see that the plugin is working, but this block is not running as often as we would like. When I save this again and again and again, for instance, it is not rerunning that. And if I come here to the project window and I'll come here to this part that is still visible and I hit play, it's not running. You can see that the debug variable is not incrementing. And then the window optimized is bug. There is a bug here. It is not working. So the hack I found to solve this, it's a hack, okay? Because if you look at the documentation for JS effects, then it says that the init block, not the slider, but the init block should run on every playback. And I don't find that to be true. The slider block should get executed after the init, but I don't find that to be true either. I guess that part is true, but the problem is that the init block is not running as often as it should, I think. So I'll create another variable, call it debug init. Save that. So debug init ran once when I saved a new version of the plugin, but as I hit the playback button, it's not rerunning it. So I think the documentation is wrong there. I meant to check this with people on the forum, but I never did. I think that's a bug. Anyway, I found a solution for this, and it's kind of a hack. The solution is to implement a serialized block. And we haven't talked about the serialized block because we haven't needed it really, but it's another block. It's available to you. And if you implement it, it doesn't have to do anything. It can be just this. But as soon as you implement it, now you can see the debug init is running every time I hit play. So I hit play and it's even running when you hit stop. Or I guess it's running twice when you hit play. I don't know what's going on there. It's kind of weird. In any case, when you run this, the init block runs and also the slider block runs. So you can see that the window optimized now it's working every time. And I can no longer reproduce the bug. I can do a full compile reset. It's working. So I like to tuck this serialized section somewhere where it doesn't bother me. I guess I'll leave it here. It doesn't really matter. But with that out of the way, now we have the three sliders working. They are fully supporting multi-channel. There is only one last thing I want to mention before we leave, and that is when doing computation with RMS, I did this mistake before and I don't want you to run into it. Don't compute with dB. Don't do the computations of adding things up, dividing, taking the square root or taking the squares. Don't do that with dB. There is another video in this channel in which I explain the relationship between amplitude and dB, but the idea is dB involves a logarithm. So when you're computing dB, you are computing a logarithm. And when you do that, all the operations change. So instead of adding things up, you should maybe, I don't remember all the logarithm rules and laws, but I think that adding logarithms amounts to multiplying the things in the logarithm. So the bottom line is, do the computation with amplitude, never dB. You did the conversion from amplitude to dB as the last thing before you are showing the thing. So that's the thing. You want to do all the computations of RMS in the raw signal. You take the square of the raw samples. Don't do the conversion for dB first. Okay, that is all I have for you today. We went through a lot. Thanks for watching this series. And that covers pretty much all I know about RMS and how to compute it. And it seems to cover the ways that people everywhere in all plugins tend to compute RMS. And that gives you an idea of how the level is of the signal over time. And you can even change the window size to do all sorts of things like respond faster or more slowly. There are ways for you to compute things with optimized versions. You can compute with even more optimized versions if you are willing to get some weird exponential thing working with the moving average. And if you like this kind of content, then subscribe to this channel because I have more videos coming up with other topics related to programming in audio effects and also to other interesting things in Reaper, also other interesting things related to programming in general. Anyway, thanks for sticking around. This has been a lot. And if you're still here, man, thank you. I see you on the next one. Bye.